Yeah, it's very interesting idea and question, Yarik. We should discuss this. I invited Lily to present dynamic phantoms paper, so maybe we can pose that question to them. Um, I mean, I am not sure, like I say, I don't know if it's a perfect solution because that phantom is still recorded outside the session, right? So there is still a little bit of a disconnect. I mean, that's a physical disconnect we can probably overcome. Maybe there is a way to embed phantom-like device during the resting session. So we have, and maybe that's the background. I don't know. There's a lot of interesting questions and to discuss. Any comments, Tanya, Joe, David?
I'm going to be talking about signal outside the brain.
Okay,
but in a different context, but that can be distorted through motion.
Right.
Someone's noise is someone's data. See, exactly.
Yeah, I mean, I guess one thing. Yeah, they also make a good point about what is signal. How do you define signal and how do you define SNR? I don't understand the definition of standardized SNR that they claim is more compatible across scanners. Because they say that the current SNR metric is not compatible, they say, across scanners because of all the changes that are happening, right? So that I didn't know. So that is something I think we could work towards, try standardizing, short focus target that's probably feasible to address, Right, maybe we should start. I think we gave 5 minutes to people. Okay, thank you everyone for joining. I'm very, very delighted to have Professor Tanya White today and giving a talk that's very exciting for me because I think, as you all know, automatic QC is very sought after in almost everything. People just want a solution that they don't have to worry about it. I think automatic QC is what everybody asks when I talk to them. So I'm very excited about this. So just a quick bio. Professor Tonya White received her bachelor's degree in electrical engineering from University of Utah and a master's degree in electrical engineering from University of Illinois. She obtained her MD from University of Illinois and then completed her residency in pediatric psychiatry and child and adolescent psychiatry at the University of Utah and a research fellowship in neuroimaging from University of Iowa. So she was an assistant professor at the University of Minnesota for 8 years prior to joining the Erasmus University Medical Center in 2009. And then she did her PhD in Department of Biomedical Engineering at the University of Minnesota in 2005 and completed it in Erasmus University in 2010. She is now an associate professor at the Erasmus MC and a PI of the pediatric population neuroimaging in the Department of Child Psychiatry. As you can guess, her research lies at the interface between disciplines of child psychiatry, radiology, pediatrics, and epidemiology. She now directs the neuroimaging program within the Generation R study, which is an epidemiological birth cohort where they have over 9,000 MRI scans in 3 waves of data collection in children between 6 and 15 years of age. And for me, 2 other important points being she was the inaugural chair of the Diversity and Inclusion Committee at the OHPM, which is doing a lot of important work since then. And more importantly, she's the editor-in-chief of the OHPM Aperture Journal that I'm promoting everywhere left and right. So I believe everyone should publish there, as I think it's a historic opportunity. And yeah, anyway, without further ado, Professor Tanya White, please take over.
Thank you, Pradeep. I'll be sharing my screen, but thanks for putting in a plug for Aperture, and thanks for joining. Feel free to interrupt me if you have questions as I go along. It's kind of an informal talk. I see some of you, but I don't see all of you. I see David Kennedy is there in the background, I think. But let me try and share my screen, make sure this all works here. Okay, do you see the slide view?
Yes.
Yeah.
Yes, and not the, I have two screens, so
We see
going
the
to be,
slides, yeah.
okay, great. So I'm going to be talking about quality assurance, but also automated QA. But actually, before you look into automated QA, it's also important to know what's the best approach, what's the gold standard. So I'm going to be talking a little bit about visual inspection of images as well. So I'm going to start out by giving you a background, a few slides just showing what I do and the problem, why for us, automated QA has become extraordinarily beneficial. So as Pradeep mentioned, I'm here at the intersection, an area. I'm actually in the area of pediatric population neuroscience, but in this intersection between epidemiology, which we hear a lot about now with COVID and pandemics, and developmental neuroscience. So I'm actually focused in this area with much of my work. And epidemiology is really the study of health in a population. So what our study is, which I'll show you in general, is an epidemiological study of child development. And there are, I think the studies are getting larger and larger these days. There's many large pediatric neuroimaging cohorts. There's those that I'll qualify as typical development. So typically they screen only, they screen out children with neurological or psychiatric problems, and they look at really typically developing or healthy children. There are clinical high-risk studies looking at, for example, ABIDE is autism, and ENDAR is a group of many, it's a database of studies. There's Brazilian high-risk cohort, and there's a large number of really large studies looking at high-risk populations. There's twins, and of course Enigma, but there's these studies that are population-based. And population-based really is trying to, the inclusion criteria is really to try and be as generalized as possible for the population that you're studying. And out of these population-based cohorts, there's only really two that are started in prenatal life. And that's the Gusto and, the Gusto and Generation R. So the Generation R study, just to give you an idea, it's a prospective cohort. So between 2000 and 2006, all women who were pregnant who lived within this zip code were invited to participate. So actually our first imaging measures were ultrasound during pregnancy. We have about 22,000 ultrasound images of the head at 3 different waves during pregnancy. And we're about ready to start our 4th wave of neuroimaging as the children are now between 17 to 19. Actually, things have been delayed because of COVID. So Rotterdam, I live in Rotterdam, the Netherlands, and the ethnic diversity of the children in our study is quite diverse. In terms of children from and families from many different, I'll say national origins, because ethnicity is perhaps something different. A lot of different national origins. and about 58% are Dutch and other European. And then finally, just going over this is just a fraction of the measures that have been collected, because the Generation R is an epidemiological study that involves not only radiology, child and adolescent psychiatry, but also pediatric dental, pediatrics, growth and development, behavior, ophthalmology. So many different people studying many different aspects of these nearly 10,000 children who've been followed. And there's still about 7,000 children involved in this study. So I came in 2009, and my task was to build up the MRI study within this group. And we have 3 different, we only got 30 minutes of scanner time, because there's also 30 minutes for the body image as well. Wave 1 was our first imaging wave, where we were just setting things up, and we were able to scan 1,070 6 to 9-year-olds. Wave 2 began around 9 to up to 12, and there we had 4,125. And wave 3, we completed with 3,740, and we've collected structural DTI and resting state. So you can see, when you're collecting large amounts of data, having some level of automated processes can be really helpful, because in rating, you have to train raters, they have to be good, you get rater drift, and visual inspection always needs to be done, especially if I go through our early protocol here of how we assessed quality assurance in the Generation R. So they're always assessed at the scanner, but also by a neuroradiologist or someone trained by a neuroradiologist to look for incidental findings. So what we originally would do, we would assess the T1 raw image for quality. We would run FreeSurfer, and we'd look at the quality of essentially the volume measures, the parcellation of the different regions, and then we'd look at the quality of the surfaces. So this was in thousands of scans, and this takes quite a bit of time. But since we had students doing this, one of the things that we found was that it's really helpful to really have the students who are doing the visual inspection trained, but also to look at specific aspects of the structural images. So the rating is a 0 to 12 scale, 4 different areas. So one is to look at the cerebellum and the fovea. This gives you actually the best detail. This is where you can see if a scan is super good or pretty good, because if there's some blurring or some movement, the fovea is less clear. Whereas the subcortical regions, they are the last. So number 3 is really not traceable, but there's got to be quite a bit of moving for you not to be able to get some measure, of the blurring. Whereas looking at other aspects, axial waves and gray matter interface, just how is there a crisp line between the gray matter and the white matter at anterior and posterior regions of the brain and axial waves. And in my experience, when we have students focus on these 4 things, it was much easier to train the students, and they could focus on different aspects. And to give you an idea of that, can you see my pointer too, or not?
Yes.
Okay. So you have the crystal clear brain, where you can actually see the fovea of the cerebellum, both anterior and posterior. And you can see this image D, which has quite a bit of movement here. You can still see the putamen there fairly well. So there has to be quite a bit of movement of an image, but the fovea are quite blurred here. So when you look at this within a sample that we tested for inter-rater reliability of this method in 500 scans, you can see that you do get more in the direction of a normal distribution. And in training students, the intra and inter-rater reliability is with ICC is about 0.88, and in inter-rater reliability, a little less than the intra-rater reliability, but overall, they tend to be quite good. So then the question is, can you automate this? And there have been there have been a few studies, and there's actually one of the main studies that I was looking at the time was one by Mortimet and al, who looked at, had an algorithm looking at the air outside of the brain. And they had an algorithm where they first removed the noise, the characteristic noise, and then looked for structured noise.
Quick question, Tanya.
Yes.
So for the rating scales, was there a specific goal the study had in mind to, you mentioned the ease of training to choose the 4 items that you guys used to rate them, but was there a specific goal or two in terms of what you wanted to avoid, like was the goal to just say, we want to make sure free surfer runs smoothly, or we want to remove all the artifacts, or was there any specific goal behind the ratings?
So there is evidence that quality of structural images, and I'll actually show you this in this algorithm, but going back to for example, Jay Geed and the NIH sample and other groups have shown that the quality rating does affect different measures such as cortical thickness and volumetrics that you're doing. And so it's to as much as possible remove bias associated with movement. And then you want the highest resolution instrument. You want an instrument that is more continuous than just yes, no. Because then you can actually also add it as a potential covariate in your analyses.
I actually have a question too. So it has to do with the free surfer. So whenever they're doing these ratings, is there any editing happening along the way? So like before you run or at the tally rack stage, or even filling in or adding control points within the image before you rerun it?
We do not do that. But one of the studies that the algorithm that I'm going to show you, they did do that, and that was the Gusto study. And so I'll show you that data, but we don't, because the volume of our scans and the lack of manpower or woman power or person power, we don't have the time to unfortunately go and to do that. So we tend to exclude.
Okay.
Yeah. So if you look at these 3 different images with good quality, medium, fair quality, and poor quality, both axial and the coronal sections, and you look, you see some change, some blurring of the signal outside the head into the noise. And that's what the earlier study Mortimet used. And this is just in color because I'm going to show you these different slides, but I'm going to do something different. What I'm doing here is, here's your original image. And here's the same image, but I just windowed the intensity level much lower so that you see, and you can see that this image is very good, and there's just essentially random noise in the air outside the brain, and also here. I mean, these are the same. This just to give a little color. I don't know why I did it, but you do see the flow artifacts here from vessels. Then you go to the medium scan. So here's the original image, non-thresholded. But then when you window it, much smaller windowing, then you really see more of what's happening outside here. And then you see it even more with the severe image, right? And in fact, one of the things that I saw here that what you would expect when you do a Fourier transform and how movement characteristically comes, is you see the ringing, the waves that propagate out from the side of the brain. And here they are all three together. So you can see with this type of windowing, the same windowing for all three. And if you look at this interface, you measure if you were to take a line and you were to go out until you hit air, to give you an example of this, what happens in a brain, and you were to look at all those kind of, here's the edge of the brain here, what happens. This is an overview of the lines that deviate from the brain. And this is actually, I think, the mean for, this is the mean for all the images. So now I'm gonna talk about how I'm thinking about this. So
what's the axis here, Tanya? The X and Y axis?
Oh, distance. Okay, so the Y-axis is signal intensity, and the X-axis is distance. I'm going to get into this a little bit more in detail, but essentially what you, well, I'll come back to your question because I think I'll explain it as I go. So if you take the edge, you start here and you're going, or you start close to here and you're going out to the edge without any type of partial voluming, what you would expect is that there would be a drop in intensity at the very edge. And in a perfect world, this is what you would see, which in essence is like a convolution. So you have, this is what the perfect world is. This is what you want to solve for. And this is whatever your signal is as you come to the edge and go out. So let me go over the algorithm because I did a number of different things. I actually ended up not yet doing this convolution, but that's how I was thinking about it because I had results in a different way that was actually quite much more simpler. So you have the raw T1 image. Using FSL, you can do the brain extraction. That's how you know where the brain is, because actually some images that have lots and lots of movement, this area, you reach the brain without even seeing this high intensity area on the outside. This is a nice image. Then using edge detection in AFNI, you define the edge, and then what you can do with that is you define the outer edge of the head. So actually the skin, the fat, the skin on the outside of the brain. Then you can determine within a region of interest where is the outer layer of the head. From using the edge detection from AFNI. So actually you're marching in from each side. Here you're marching in until you reach the edge. But if you reach the brain, then actually there was something that went wrong. It actually means it's very likely a very poor image. So it's actually these X lines in the X dimension coming in from both sides and extracting this curve. How do these look? Is it like this? Is it like this? And that's what these are. Then once you have these lines, so I did 3 different approaches. One was, I said, oh, you know, there's waves. I'll do a Fourier transform kind of the in the one-dimensional line, and I'll see a certain peak frequency characteristic as opposed to, more of a white noise type frequency spectrum in the noise outside the brain. So not using the very edge. So you have to step away a bit and then using that. I said there's going to be some type of structure. The second is, how quickly does the gradient descend from the side of the head down? And kind of looking at this, the quicker it descends, the less noisy it is. This spoiler, this worked the best. The other is the integral. I'm going to look at the area under the curve from how quickly it dropped down. And using those 3 different techniques for 3,053 images, this was the histogram of the Fourier approach. You get a really nice normal distribution, but the gradient was more skewed. And the integral approach was also even more skewed. But then the question is, which one works the best? So the first test was, I'm going to predict which of the poor quality T1 images. So if the image quality is poor, then the MR operator repeats the T1 image. So how well can this algorithm detect which scans are repeated? So we had 2,758 scans that were not repeated, and we had 294 scans that were repeated. And I'll show you an area under the curve for using those scans for those different approaches. The Fourier didn't actually work very well. I was quite disappointed, but the area under the curve is 6.19, but the gradient 0.946 and 0.924, these were actually fairly similar, worked really well at predicting which scans were going to be repeated, or a good area under the curve.
So is the prediction based on the bad scan from the before the repeating, right? Just to be sure.
I'm sorry, what? So the algorithm was done after all the scans were collected. So is that your question? So it wasn't.
No, my question is, the prediction, the model is trained on bad scans, right? Bad scans.
Actually, this is just this is an ROC characteristics. It's not really. You could choose a number for what so I use the word prediction. I probably shouldn't use that. This is the receiver operating characteristics of how well can it identify based on a different gradient. So so you can choose a different gradient, and then you can have a high specificity or a high sensitivity, if that makes sense. So you would.
Right. No, so computing ROC still requires labels for each image and the
Yeah.
feature extraction has to be performed on scans that were acquired prior to repeating, right? That's the whole point, right? You want to
Right.
detect if the scan was bad based on the original scan and not the repeat. This wanted to double check.
Oh, right. Yes. So it was based on the original scan.
Right. Okay. Cool.
Yeah. No, that's a good point. Mostly because actually, so
So Tonya, sorry, just a follow-up question there. So you said that the operator redid the scan. So what was that? Was there any specific criteria that the MRI tech used to repeat the scan, or he was just eyeballing the image and saw it was bad?
it was eyeballing the image
Okay.
because we had so many people and many of them were the radiology techs
Okay.
who were very difficult to train.
Yes, no, I know, I'm aware of that. So yes, okay.
Yeah, don't quote me on that, but
I have a interesting question. Well, not sorry. I don't know if it's interesting or if it's simple. I don't know. But so would the goal be to use this algorithm on scanner so
Yeah.
that it can automatically, oh, wow, that is so cool. Okay.
yeah, that was to give an extra information. So what I did is I went in and I said, okay, where I'm going to look at the most scans that were misclassified. So when a scan was repeated, but the gradient said, this is a good scan. And if I do that, so let me go through this. There were 5 of them that actually were good scans that did not need to be repeated. So the algorithm did a better job than the operator. There was some operator error in getting a scan. There was some that was would be rated fair, but didn't have much noise outside the brain for some reason, but the scan was fair. There was one scan which should be removed, but the algorithm wouldn't pick it up. You could add something to say, is the whole brain in there? But I didn't do that. But a child moved, and so you had part of the head cut off. And so that would need to be repeated. And the algorithm as it was couldn't pick up that, but you could actually, that wouldn't be too hard because there needs to be air above the top of the skull. And if there's no air, you could flag it. So in essence, there were a number of scans where the AOC could actually be better. Then there was the question on what if you repeat the scan? Is it worthwhile to repeat the scan if you have a child with a bad scan? So there's a number of them that were repeated and I don't understand. So here's the gradient for the automated quality assessment for scan rated poor, the 294 here. And you can see here's the best manually rated scan here. And here's the second scan when you repeat a scan. And the good news is for children, if you repeat the scan when it's bad, it usually gets better. So that's good news. So what we've done in Generation R is we've actually removed this step here and we use the auto QA. And we still do visual assessment of the free surfer quality assessment, but we don't do, and we still do incidental findings, but we remove this step and it's probably a little bit redundant as well. So, but we also can use this measure as a covariate in the analyses.
I actually have another question, and this may be a really dumb question, but like, why are you using, or why is free surfer being used as a, I guess, technique for quality assurance or QCing?
Oh, no, we just run FreeSurfer, but we want to make sure that the quality of the FreeSurfer is good. So we're testing it.
Oh, okay.
But we're using the auto QA to assess the raw image.
Okay, that makes, okay, got it. I'm fully there. Got it.
Helping assess the raw image and whether it needs to be repeated or not. It's not on our scanner yet, unfortunately. So hopefully we can get it there before starting the new wave. But I also wanted to, so in Generation R, we've had 2 waves. So let's, the other question is, how well does this work on other scanners? And this is where I'm going to get into, especially for the Gusto study, I'm going to get into some of the challenges, because Adam Thomas said, hey, can you get this measure uploaded on MRI QC? Which I said, yeah, this would be great. But it's tuned for our scanner, and there's a fixed, so we have the sequence the same. It's an epidemiological study, so it's run the same sequence on every child that comes in, and it's a GE 750 wide bore scanner that we use. Doesn't need to be a wide bore, but and the threshold that you set for what is a good scan and what is a bad scan is dependent on the scanner. So, so here's the Generation R first wave, here's the Generation R second wave, so 1,070 scans, 3,940. We had the National Institutes of Health, genetics research, so Philip Shaw, and 442 images from his group. And then from the Gusto study, my counterpart in the Gusto is Anki Kui, and used 252. And so these are really young children. So the age range here is 4.59. NHGRI are older. And then we have 7.9 and 10.1. And you see the standard deviation is quite narrow because we are collecting imaging waves, and there's the age range. So how does it work on other scanners? Well, NHGRI has an area under the curve of 0.88 for their raw T1 images, so it's actually quite good, not quite as good as what we had. They're also using a GE scanner, and Gusto, which is using a Siemens scanner, has an area under the curve of 0.82. Now I'm going to end with one more slide, then I'm going to take some time to really walk through, because it's kind of comes back around to one of the key aspects of quality assessment, but also it'll touch upon a question that was asked earlier about the utility of QA, what you do with it. So I'm going to start with Generation R Wave 1. So it's hard to see probably, but these are brain lobes here. And this is cortical thickness, mean cortical, this is each measure here, and these are correlation coefficients. So this is a correlation coefficient between the automated QA measure and the mean cortical thickness for each of these measures. And right along the x-axis, so 0, this is all the children. But as you go this way, the child, each consecutive time the correlation is run, a child with the worst image quality is being removed. So for Generation R1, we had 1,070 children. So here's the correlation of 1,070 children. It's about 0.5 with the right frontal and the left frontal lobe here. That's the correlation between the automated QA measure for cortical thickness in those lobes. The next point, the child with the worst movement, or the lowest gradient score is removed, which is more movement, and then the correlation is rerun, and so forth. And so actually what I was hoping was that it would kind of go quickly down to 0 and then it would go flat, because then you could have a certain cutoff of where you knew quality was good enough that it got to 0. It kind of had, for the first wave, more of a linear. For our second wave, it changes a bit. There you see a more quick drop off and then a plateau, but still here there's a relationship of 0.2. And then once you get down to lower numbers, then it becomes much more noisy there.
Sorry, Ed, to interrupt. What's the focus on zero correlation coefficient? How does that imply a good working algorithm?
Oh, it'd be nice to have at some point no correlation between the auto QA measure, which is outside the head. So it's the gradient from the edge of the skin to the air, to that not to be correlated with a cortical thickness measure inside the brain.
Why is that? That I'm not following, because wasn't that originally trained and optimized to detect issues in quality?
Yes, yeah. Well, yes, it was trained, but not the measure of cortical thickness.
But thickness has a direct relationship with quality. Actually, depends. It depends on how well you QC'd the free cipher outputs, you know?
And I think that's what this shows.
So are you saying that thickness value follow the quality of the free cipher output?
The automated quality assessment follows the cortical thickness measure.
But the quality assessment was based on the raw T1 MRI, right?
Right.
They was not based on any of the measures that is outputted by free cipher, which is one of them being thickness.
Right.
So I think I'm missing a bit of a link. Why correlation between the gradient score?
Why I want it 0, or why is it 0.5?
I mean, why is this relationship? How does this relationship help us with quality assessment? That's what I'm trying to follow. It seems like there's a few leaps that are happening here, you know, our assumptions that need to be more explicitly stated.
So I mentioned what I was hoping for. So maybe what if I were to say, what if, so this is 200 scans here. Let's say at 100 scans, let's say the image that this curve wasn't more of a linear decline. What if it went down at 100, it was 0, and then it stayed constant from 0 onward? Then I would have said 100 is the point where the cutoff that you should exclude the individuals, because you have a relationship between quality and thickness of the cortex.
Yeah, I guess that's where I'm stuck. I guess we need to see that, right? Because these are all healthy people. If you plot the distribution of thickness in these ROIs for bad and good scans, and maybe you've done it and then you believe it, but we haven't seen this stuff.
They're not all healthy people. They're population, people from the population.
Right. In that case, that may be a bit of a tough assumption, because especially if free cipher outputs were not manually QC'd. Because basically, I mean, free surfer is generally wrong in my personal opinion, unless you manually QC it and at the population level. So this may be an assumption that can be explored a bit further. I'm not saying it's wrong, but this is the first time I've seen it used.
So what is, tell me what the assumption is?
Basically, I'm trying to, here you're using the correlation between, let's say, median thickness in left parietal ROI,
Yeah.
on the gradient score your algorithm computes, right?
Right.
So that means that you're taking the thickness values in these ROIs as a proxy for the quality of the structural MRI, which is an input to free surfer. Or am I getting it wrong?
So the measure of the gradient is not in the brain. It's outside the brain.
Right.
It's from the edge of the head to the ear on the outside.
Yeah, I think what would be useful.
I wouldn't expect that to be correlated with cortical thickness unless there were some, I don't know, difference between, yeah, the skin,
Actually, so this could be, go ahead, Alex.
Yeah, I'll put some 2 cents here. Yeah, no, we've worked on some data looking at free surfer, and cortical thickness from free surfer is extremely sensitive measure. It's of the free surfer measurements, it's the most sensitive measure for any little motion. Even if you have zero motion, you do have a lot of variability of quality of cortical thickness. The other measurements of free surfers are pretty robust and do very well for measure. But what I'm really liking here, Tonya, that you're showing us, that even though you're showing that you're being very exclusive and picking very good participants, when say you exclude 400 participants, there is still free surfer cortical thickness is still showing a correlation with your measurement of quality. And for me, that's saying that free surfer is still very sensitive to the quality of the data. Even though your measurement is something looking outside, you still see some relationship. And that's why you kind of plateau around 0.2.
Yeah.
And
Right.
going a little bit deeper, Pradeep, I agree with Tonya. These are, her measurement of quality is somewhat, even though it's the same image, it's somewhat independent of the free surfer cortical thickness. So she's just looking at the relationship between them. That's my understanding.
Yeah, so I guess I'm trying to, I am yet to believe that, so to say. I mean, not saying this is all wrong, but I don't think free surfer as a cortical thickness values in these ROIs track the original quality of the input T1 MRI, because even in, go ahead.
I think I see. I'm not using cortical thickness here for quality measure. That's not the goal. The goal is the other way around, to look at if the quality of the scan affects the measure of cortical thickness. So the cortical thickness here is not really what I'm using for quality.
I have a question just on that really quick.
Oh,
sorry.
Oh, is it the same? I just wondered if, for Pradeep, if that was, if you thought that I was using the cortical thickness as a quality measure.
Yeah, so what are we trying to analyze here in the 4 plots? I guess that's where I'm trying to understand the point of plotting them, to be honest. Sorry if that sounds bad.
So what I will say is that the Gusto study, and then I can't see who asked the question. I think it was, but in any case, the Gusto study did use control points, and they collected multiple images that so the cortical thickness that they're showing is, it's still somewhat correlated, but, and their sample size is much lower, but it's different than, for example, Generation R. And although we had nearly 4,000 images here, and the NHGRI is also a smaller, much smaller group. Okay. Who was asking a question? I can't.
Oh, that was me.
Okay.
Yeah.
Yeah, okay.
Another potentially dumb question, but how are you detecting whether the cortical thickness is accurate? Like, is there a separate measure that you're using to be able to determine whether it is inaccurate or accurate outside of free surfer?
No. Well, so for these images here, this is 1070, or it might have been actually a little less, because not all images, the really bad images, couldn't be reconstructed via free surfer. So I actually would have to look up the exact number, but we didn't run them on just, we ran them on all free surfer data that could be constructed. So quality assessment occurred, but that you don't see in this image, if that makes sense, because this was more of looking at, if you can reconstruct it, what's the relationship?
Got it. Okay. Mm-hmm.
But we didn't do another like image processing algorithm like Civet or something else to say, okay, what is the cortical thickness measure using a different approach?
I see. Thanks.
So finally, so you can have a quality rating scale that can be automated. And hopefully this can be integrated in the MRI QC, because there's other algorithms that are doing this in MRI QC, and then Rosen from Ted Satterwhite's group has also used the Euler number from FreeSurfer to show that that works. Or you can combine different measures, and I think MRI QC is doing that now to use some type of machine learning that you can use multiple measures to get a better prediction. So the automated rating can potentially be used as a covariate. We have done that in our population-based studies, and then implemented at the scanner, because sometimes you see scans that that are redone where they actually don't need to. And for us, when a T1 is redone, it means we miss usually the resting state scan. And that's the end of my talk. Here's just a brief visual of resting state topography from our first wave of movement over every TR and participant ranked in on order of mean movement to get an idea of the topography of movement for our resting states. But I haven't looked at the you know, I'm sure that the auto QA will predict also those who sorry, I lost my train of thought as I was stopping to share my screen. Predict those who will do poorly at the structural QA may predict those who also do poorly at resting state.
Oh, they certainly do.
Yeah, they certainly, actually there's evidence for that, yes.
Say that again, I missed that point, Tanya.
That children who move for structural are going to move for resting state as well.
Okay, got it, yeah.
Although if you repeat the structural, it does get better. And when I was in Minnesota, we had a mock scanner where I had some engineering students. We took headphones and we had this device with LEDs, and we had a camera that was, so we could measure kind of movement by these LEDs here. And we were looking at head movement during training, and starting with the structure, starting with the resting state or the functional images or a movie was actually turned out to be not as good as go ahead and just starting with the structural image or task fMRI. So it's good that they, it takes them some time to assimilate in the scanner environment, and then they get better. But then for children 8 to 12, after about 30 minutes, you just see the movement go up. It's not surprising. And the one time that I had lots of movement in the scanner, I was in the scanner in Minnesota many times. And it was when I was watching Shrek. When I watched Shrek, I moved a lot. So any
Big
other
movie.
questions about this? I mentioned one of the challenges. So we were going to apply this in the Rotterdam study, which is a population-based study here in Rotterdam of aging, in which there's like 15,000 scans that have been collected. And their contrast is much different, much narrower contrast between the noise outside the brain and that inside. And we were just having, we haven't worked on it a lot, but we were having some challenges. We were working on an algorithm that could define the best threshold for different scanners, and without having a test set, without having to give it a test set. Can we do it? Can we calculate it and say you run it and then match it to to a certain distribution of what you would expect?
So Tonya, I had great talk. Thank you. It was very nice. Yeah, I know I had actually been introduced to your work. Jonathan Dyke from Cornell told us about your work.
Yeah.
He was showing us about this. We were really excited. So one question. Okay, so you will have two questions. So first, you said you have it set up in your scanner, and so
No, we don't yet.
Oh, you don't yet. Okay.
No, I have to talk to the physicist to get it set up.
Okay, so in let's say in an ideal world, you would have automatically, okay, run the scan, pushes to another computer, that one runs your algorithm automatically, gives you a number automatically, and then it gives, not gives you a number, gives the text say good to go or bad, repeat or something like that automatic. So be able to do that, it has to be fairly quick. So how quick is your algorithm?
It's actually fairly quick. It's on the order of minutes. So you could be running your DTI scan. So that's our second scan, and you would have the result at the end of the DTI scan.
Okay.
So it's not all that time consuming for one image.
Okay, good. Yeah. No, so
actually, it may be under a minute.
Okay.
I would run it all at once, and so 4,000 images is run overnight.
That's quick. That's very, very quick. It's very. And
so the other thing is how I envisioned it is that, so there were the operator looking at the scan. If this would give them additional information. So if they're about ready to repeat a scan, but the scan says this is good, or if it says this is bad, it could flag those differences to say, look closely at this image before you make a decision. But
and so yeah, so that's really cool. Yeah, no, I'm working, actually I have another project that we're actually doing automatic QC of functional data, and so that would tell. Basically, it tells the operator, okay, if you have like a 10-minute run, by just running 1 minute, and this is what I say, once a mover, always a mover. And so if a child is someone moving too much at the beginning of the scan, you're basically going to lose the whole scan. And so that tells the operator, hey, stop the scan right now, talk with the child or the participant, hey, you're moving too much. And then they repeat the scan. But you don't have to run the whole 10 minutes, you just run 1 minute of it, and then you can get a warning. And so we have a tool that we developed. It works for GE scanners, not for Siemens yet. And so that's one thing. And what you have is really cool. It will be a good complementary for structural scans. But
I was wondering if it was going to be obsolete, because I believe GE has a sequence now that it oversamples the low frequency, if I'm not mistaken, in K-space, and then adjust the scan time up to the
that's my
point
follow-up
where you-
question.
That was going to be,
That was my
yeah.
follow-up question.
Yeah.
So ABCD study is running the sequences that are, it's not, I don't know if it's not exactly the sequence you were talking about, but they're using what's called the prospective motion correction sequence. So that used with the VNAVs. And so that works for Siemens, GE. I'm not sure if it works for Philips.
Are you talking about fMRI?
No, structural scans.
Okay.
So they have what it is they're collecting data in K-space, and then between each TR, they do a quick functional scan. They collect a really low resolution 8 by 8 by 8 millimeters, so they can have a volumetric navigator. And then what they do is they adjust the K-space collection by doing this motion correction of the functional scans. Okay, and then what they do is they notice that if there was too much motion between each TR, what they do is they repeat those K-space sampling at the end of the scan. So they make the scan a little bit longer. So you have variable amount of time. Of course, there's only so much you're going to repeat. And we at the, I'm one of the coordinators of the Healthy Brain Network here. And so we're usually using the VNAV scan, and we're very happy with it and compared it to traditional MP-RAGE, and the results are much, much better. However, what we saw is a lot of the QC measures that are typically used, and your work is actually looking outside the signal outside the brain, and that's typically what's used for SNR. But for these prospective noise correction signal images, there's actually a lot more noise outside the brain than in the brain. The brain is a lot better, more robust to motion, but that's my theory is that since it's adjusting the gradient, it sacrifices quality outside the brain, which we don't care about anyway. And so how would your I'm already asking something I probably know the answer. You haven't tested your technique on these images, on these sequences.
No, but I mean, the technique, because you can visually, all you have to do, so you have a load an image up in any viewer that you want. Let's say FSL eyes, you load it in. Then you have your low threshold. It goes from, I don't know, 0 to 6,000, 7,000, 8,000. Change it to 100, 0 to 100 or something. And so your whole brain is white, but then or 100, 200, depending on the if there's lots of noise. So I would look at the characteristics of the noise. Is there structure within the noise that's different? And if it's not, then I don't think then the algorithm that I have isn't going to work. But then maybe there's other algorithms that work for those. I mean, the question I would have would be, you have a built-in quality in terms of how many times they've collected how much they had to adjust the.
Yeah, there's one thing. This is I'll send you a paper that we wrote that was actually on this. What's beautiful about this sequence is you actually get a frame-wise displacement measurement for the structural scan.
Yeah.
So you do have a thing that you can see, and then use that to relate how much motion it is.
And you have the length of the scan. So this would be something.
But you get like a motion parameter, just like you do in fMRI. You do get motion estimation during a scan, during the structural scan, and you can use that as a proxy. But what I think for your technique, I think it still will work for VNAV, and it goes straight to the point that you need to adjust per scan, and so per scanner, but you probably need to then adjust your threshold per sequence. And so this one is probably going to show a little bit higher, but the bad scans from the VNAV are actually going to be higher. So it just needs to adjust the threshold. So on that point, my question is there a way for us to be able to get a hand of your algorithm or code for, and then we can, because we have data of people who did the MP-RAGE, we have test-retest data, people who did the MP-RAGE and the VNAV sequence during the same session. So we actually then compare directly these two sequences on your quality control.
Yes, there is. So it was written in MATLAB, but a couple of years ago, I I changed and then moving over to the world of Python. And
I'm fine with MATLAB. Don't worry. I know Pradeep's gonna get mad. I'm a fan of MATLAB. I
No,
don't care what.
No,
Okay.
I was gonna say I implemented parts of this algorithm in Visual QC because I don't know if you guys have seen Visual QC can help with structural MRI scans. It does give some different ways of looking at it, emphasizing the areas outside the brain to catch all the issues with ghosting and few other artifacts to make it easier to capture, right? So to do that, I implemented parts of this. In fact, that's another question I was going to ask you. That two questions actually. Besides the, if you share the data, we can all try optimize our techniques, especially more machine learning oriented ones. You know,
share the data or
because
share the code?
data more so than the code, because I wouldn't have done it this way, to put it, because I think there's one thing that is very clear to me from this talk. This has been a fantastic talk, by the way, is that we need a standardized rating protocol to assess the quality of the anatomical scans. I think this is a good time. We have enough studies and whatnot, a couple of papers already. So, and two, this hasn't been based on a cross validation, right? Your ROC calculations are typical biostats way, not out of sample cross validation, right?
Correct.
Yeah. So yeah, because in the way you want to implement it in scanner, you want a single subject prediction, and that needs to be explicitly evaluated in a way. So, and the final question, more existential, is why not just train the operator to look at the T1 MRI scan and decide whether it's good enough or not? Because if you just lay out the mosaic, you can tell almost all the typical problems with T1 MRI right away with a trained eye, right?
Say it again, what?
So the purpose of the algorithm is to instruct one of the purposes is to tell the operator it's not good enough, repeat the scan before the participant leaves, right? They could assess that in like probably 20 seconds or 10 seconds when they just look at the mosaic of the T1 MRI on the which they can on most of the scanner interfaces nowadays, right? So, and that is typically more accurate than the algorithm, is it not?
No, it's less that it was less accurate.
Or be if they were sleeping or not
Well,
paying attention.
what I can say is that there was a mismatch. That there were 5 cases, and that's quite a where at least 5. I didn't go through all of them, but because I think some of them are going to be gray areas, and where it's kind of fair and it's right on the border. But when you look at the ones on the extreme, those were clearly operator errors. They repeated a scan which didn't need to be repeated.
Yeah,
I was gonna say the same thing. Just from at least my experience, it's not. I don't think it's as black and white as you're presenting it. I think it is for the extremes for sure that the operator will be able to catch those, but for the gray areas and sometimes people don't actually know how much motion is too much motion, or there are other artifacts as well. Also, it helps when there are algorithms that rely on the data itself, like gradients within the data, or intensity gradients within the data. And there are some errors that users just can't catch because of that. So like, at least in my experience, I have written an algorithm that's based on intensity that's looking for like white matter hyperintensities. And there are just some intensity biases that a user just can't really detect, I guess. But anyway, I think something more objective is better than just relying on a person.
I agree. visual inspection is not going to go away.
Oh, yeah, exactly. I'm just curious because I think that motion can be easily cut visually. That's one of the big artifacts.
So when you have a large population-based study and you have different radiology techs coming in, that's where the problem is. If you have your own, if your own people doing it, this is also, even within an individual, there can be some drift over time, and the algorithm, unless the scanner has drift, which I think is what you started off the conversation with about stability of the scanner. And we were doing we do a phantom, an agar phantom every morning. And we had one time, we run the protocol by Gary Glover and Rob Friedman and Glover. There's an interesting paper that was used in the FBurn. So we've been running that protocol, and we had one time where it just got terrible. I mean, we called the tech, there's nothing wrong with the scanner, everything's fine. The phantom went bad. Our agar phantom somehow went bad. So.
Wow.
Was it bad just for that day, or is that just it degraded finally?
It degraded.
It just okay.
Yeah, and you saw. I mean, just
phantoms, if they're from agar, that it could go bad, right? And people run. But how did you figure out that it's phantom? What metric kind of gave it away?
Put it in a different scanner.
My Zoom made me so not quiet. Yeah, how did you figure out that it's bad? Was there a specific metric which would kind of prime you?
Well, we scanned it in a different scanner.
Okay, and it gave you different results.
You have two. We have more than one phantom, and the phantoms can be shared by different scanners. And so either you had multiple scanners all going bad at the same time, or
But bad was it lower homogeneity metric?
It was just a change in the signal, global change in signal intensity. So what the you follow the SNR, and then suddenly, so if a coil goes bad, and in the Glover and Friedman paper, they do a really nice example showing what happens when a coil went bad, and then they were able to use the phantom to pick that up. But for us, it just kind of, you had a sudden intensity, and because we're doing it every day, we had a really nice standard deviation, and then suddenly, boom, it just dropped low.
Okay.
Maybe someone dropped it, maybe, who knows what happened. The phantom went bad though. Someone's got chicken. You're sitting out in your backyard, is that right?
Yeah, there are chickens there.
Okay.
And they want to be let out.
When I first saw you, I thought, oh, you're calling in, you're out camping somewhere, like, because it looks like there's a tent over your head. So
Sometimes it rains, so had to have something covered.
Yes.
Any other questions? Maria, Ali, David? Everybody has to ask at least 2 questions. That's my rule.
Okay, I'll ask 2 questions. You said you would have done it different, Pradeep. Can you tell me what your thoughts are in terms of how you would have done it?
Yeah, so first of all, it starts with the rating. the way you chose the 4 items was very interesting. You know, I already touched upon it with a question about the purpose of choosing those 4 items, and also the summation of these ratings. I don't think it adds up to a continuous ordinal rating. That's another interesting discussion to be had.
So there was the visual rating, but then the auto QA. So
that's a
would you
gradient.
have done the auto QA different?
Yeah. So I mean, I think that out of sample cross validation is necessary. You know, for example, with the predictive model. So that means it needs a good target. Good target meaning I would basically, I mean, now we can redo it because it's already done. What I would do is to do the rating a bit more, what you call broadly, in a sense, no, not just motion and PRYs, but also typical other artifacts that are typical in T1 MRI. You know, you refer to that more Martmet. I don't think I'm pronouncing the name right. It's a great paper. I read it to implement image quality metrics, right? So we'll probably try tick all of them. A few things I would do is to not just target the overall quality, good or bad, but also specific artifacts. I think that's it's a useful thing. You know, ghosting is an important thing, right? Susceptibility
and there are
issues.
papers picking up other specific artifacts, so the ghosting and the
yeah. So the reason being, we discussed this
inhomogeneity.
already. The reason being we discussed the issue of operators not paying all their attention to the subtle issues, because that's where we really need help, not just saying, hey, it's usable, but also there is some issues. Does it matter for the particular goals of that RA/PI for the project, right? So what we need is a full assessment of the scan, not just is it usable for free surfer or not, right? It's free of motion, free of ghosting, free of susceptibility. So that's the kind of approach I would go for if I had all the money and resources to target. And also, yeah, the cross-validation thing I think is, and you have wonderful data. I mean, although I may have wonderful data from like 4 different data sets that could be used to do a lot of interesting things, you know. So that's what I'm interested in, you know, if it is possible to collaborate on these things.
The Generation R study is run by the Department of Epidemiology, and they are very strict with the data.
Right. Yeah, maybe we could redo ratings on few other public data sets and try target the models towards, you know, because it's a anatomical is captured in almost every study, and you know, I think we need something like this going forward. So I'm happy to work towards achieving this. One of the things I would propose to the SIG is to try standardize the protocol. I think it's high time we need that. And so people can target different algorithms towards it, you know, not just go with what is out there, but also like, hey, can we improve the accuracy? What is accuracy, you know, and that depends on the goal. Like I said, is it just usable or not, but also is it free from certain artifacts, right? So
right.
Yeah.
So I think probably, I mean, for this algorithm, getting it worked out and then integrating it into MRI QC, and as you said, I agree that there could be lots of other different measures that could be really helpful, and then taking approach, whether it's with a kind of a training set or whether, you know, supervised learning approach. Yeah, so having it, so the MRI, integrating with the MRI QC might, it seems like a possible approach. And then you have everything embedded into like one program that you can run on the data, and you get all the different measures out. And then the question is, what do you do with all of them? But it would be nice to have something quick that could be run at the scanner.
Yeah, so these IQMs are actually rather easy to compute, you know, except when there is like heavy registration or other parts are involved using older type of software, you know. So we can try optimize it, of course. But I think like there is a lot of retrospective data that these algorithms could be applied on. So speed would be on the scan, real-time algorithm would be great, but also even if they're not as fast, if they're accurate, I think that they will also be quite useful, you know, for example, on ABCD, HPN, and other data sets. So we probably need a multi-pronged approach. Start with an accurate algorithm and try optimize it for on the scanner implementation. Yeah. Any thoughts, David? I don't know if he's still here, but
David,
Yeah,
are
I'm
you
still
there?
yeah, I'm here. No, nice talk, very informative. I'm just absorbing. Don't really have any questions. Sounds great. I'm getting it into the platform where it's easier to do them all because there's no one metric that rules them all.
Yep. And we saw that when we tried it on the Gusto study, and it wasn't quite as good. So you might have to have some tuning for each individual platform and sequence. Yeah, that was raised too.
what do you mean? Like the quality differs across different scanners or different geographies or sites?
No, the contrast and the metrics that you're measuring will differ to some extent between different sequences, and you have to be able to account for those differences.
Oh, acquisition parameters and yeah, see, yeah, exactly. So that's right. The performance does depend on these configurations too, right? So it'd be interesting to understand how that differs, so to say, you know, right. That's why open data and open rating that other people can target algorithms, I think, would be wonderful. Cool.
And the question about how they're doing the ABCD, I have the ABCD data, but just the process data. Be interesting to actually look at their raw T1 images and just see what it looks like.
Yeah, I mean, if resources permit, I would like to get them at least like 300 to 500 of those scans rated with a couple of raters. You using a protocol using the best version of the protocol that we could apply today, and then release it. Hey, look, target your algorithms, you know, detect motion or rate the level of motion, not just detect it, but also rate it, you know. So that would be a very interesting challenge to run. But there's not enough resources. That's the biggest problem.
Absolutely.
Yeah. Maria, Alexander, any questions before we wrap up?
Okay. None here. Thanks.
Okay, cool. Yeah, so I would like to follow up with you, Tanya, later, you know, if it's possible to share or collaborate on the data, that'd be fantastic, you know?
Sure, yeah, I'll send a link to a GitHub account with the data, or not the data, the code. Data is challenging, trust me, I've tried. In fact,
not just Generation R, but like any other thing that could be shared, you know,
Gusto is in the same boat. I think the NHGRI data, I think the NIH is moving towards open data as well. So I think through NDAR, you can, and actually David Kennedy is probably the best person to talk about all the different sources of data that you can get your hands on. I know our Mind Research Network consortium data was open, and that's through NITRIC and through COINS.
Healthy Brain Network. we heard already mentioned today, that would be good to look at.
Yeah, that would be good. They actually want to apply it. So
That's probably one of the, I mean, if they're here, they can say it, but it's probably one of the openest, widest, broadest sets. You know, it's kind of generation R-ish at an older age, but very comprehensive assessments. So,
and
Very
abide.
good.
Yeah.
I love
And
Abide.
that-
Won't say anything bad about Abide. The challenge with Abide is it's a little bit, it's many different sites, and we know has huge quality variations in it. You know, in general, of the 1,200 subjects, most papers do some quality assurance and usually only use about 800 of it. It'd be nice to have a more systematic assessment of how and why you choose the good subset of Abide. And it has challenges because it's many multi-site studies. So and it's practical to look at that. Whereas the Healthy Brain Networks, the ABCDs and things like that are a little more controlled studies, which have better characteristics. So that's good to test too. But again, we also want to be able to come up with protocols for new studies, to be doing prospectively, so that when they do get put back together into bigger studies, they're better controlled. They're easier to know what the situation is.
Yeah, fantastic. Awesome. Thank you so much. This is all being recorded. I'll upload